Hi everyone, it's Sorkin. Today we have a problem when we are given points in the coordinate system and we need to find the minimum cost to connect all these points. So for example, let's say that we are connecting this point, let's say that this is the minimum, right? And the cost in our case for connecting 2 points is the Manhattan distance. Unlike the Euclidean distance, which is the direct distance, Manhattan distance is the distance between absolute value of x and the absolute value of y. For example, in this case, between these 2 points, first and second, right, the Manhattan distance is this one. So delta absolute difference of x plus absolute difference of y. We are going to solve this problem using the minimum spanning tree. And let's remind ourselves, what's the minimum spanning tree? Minimum spanning tree is a tree, is a acyclic graph where all vertices are connected and the sum of the weights are minimum. So let's write down those characteristics. Is a cyclic, right? A cyclic graph. It's where all vertices are connected. All vertices are connected. And also where the sum of weights, right? Sum of all weights is minimum. Okay, there are 2 ways how we are for the minimum spanning tree. There are 2 algorithms. The one of them is the Prim's algorithm, right? And another one is the Kruskals algorithm. So in our case, we are going to use Prim's algorithm. So to apply to our problem, right? In our case, we have in the coordinate system, we have 5 points. Let's say we can say that the 5 vertices, right? 1, 2, let's say 3, 4, and the 5. And then we need to find the minimum way. So it should be acyclic, there should be no cycle, right? And we need to find the minimum weight, how to connect all these vertices. So for example, one of the way, right, to connect all these vertices, maybe this is the minimum weight. So what are the other ways we can connect? We can connect, for example, this way, right? This is another way how we can connect. So we have 5 vertices in this case, and 1, 2, 3, 4 edges. So, and in this case also all vertices are connected. But which one is the minimum? So in our case, in the Prim's algorithm, right? So the idea is that we are choosing any random vertex. Let's say we are choosing this one like it's our first vertex, right? And the first thing that we do, we calculate the minimum distance from this vertex to all other vertices. So we are calculating minimum distance. In our case, we are calculating the Manhattan distance, right? We are calculating to this one, we are calculating to this one, and so on. And whatever the minimum, we are connecting those 2 points, those 2 vertices. So for example, in our case, right, first we are going to calculate from 1 to all other, 2, 3, 4, and 5. So let's say that we have calculated and that the minimum distance is this one. So we are calculating these 2 points. Since we already visited one, right, so what we are going to do implementation wise, we are going to create 2 variables. So first one, in order to always get the minimum, the weight with the vertex with the minimum value, we are going to use a heap, minimum heap, right? Minimum heap, where we are going to add all our vertices with their weights. And whatever weight is the minimum, we will always, so minimum heap will give us the vertex with the minimum weight. And the second one is we are going to create array of Boolean. So Boolean with the size of our n, with the size of our vertices, where we are going to mark each visited node, right? If we visited this one first, we are going to mark that as visited, so not to visit that one more time. So now let's say that we have visited the second one. Now also from the second one, we are calculating the distance to 3, to 4, to 5, and so on. We have calculated for the first one. Now we are calculating from the second one, and we are connecting whichever distance is closer. Let's say that we have calculated and the closest distance is again this one, from 1 to 5, right? We are connecting from 1 to 5, right? And we have, at this point, we visited 1, we visited 5, So we are marking that as 1 is visited and the 5 is visited, right? Adding to our Boolean. So we won't visit them again. So now we are again calculating from 2, we are calculating again from 5 distance to 3 to 4, and we are calculating to 3 and to 4, right? So let's say we have calculated, and also we have the distance from 1, right? We have distance from 1 to 2 and the 3. So now we see that the shortest distance is from the next shortest distance is from 4 to 5. So at each step we are selecting the vertex with the minimum weight, so with the shortest distance, right? So we are selecting this one, right, from 4 to 5, and let's say that we are calculating again the distance from 4 to 3 to 2 to 1, and let's say that now the shortest distance is from 3 to 4. So now we are adding also these visited nodes, right, 4 and 3. And at this point we have already, so we have calculated the, let's say this is the weight 1, right, weight 1, weight 2, weight 3, and the weight 4. So we have, so it checks all our points, right? It's a acyclic graph, there is no cycle. So all vertices are connected, yes. And also the sum of the weights are minimum. Yes, the sum of the weights are minimum because we implement here Prim's algorithm, and the sum of the, at the end, we are going to have and we also use the minimum heap, right? So at each point, we are selecting the weight, we're selecting the vertex that has the minimum value. So the sum of the weights are gonna be minimum. Okay, first thing that we are going to do, we are going to create a minimum heap. In Java implementation, it's a priority queue. So we are creating a priority queue, right? And so what we are going to compare, we are adding to our minimum heap, we are adding vertex and its weight, right? So we are going to compare our weights. So we are taking A and B. Let's say we have A and B vertices, and we are comparing A1. So A1 minus B1. B1. Okay, so we are comparing our weights. And the next one is we are going to create an array of Boolean where we are going to store our visited nodes. So let's call it visited, and it's a new Boolean. It's gonna be the size of how many vertices we have, right? In our case, we have points. Let's take the length. So we have as many vertices as we have points in our coordinate system. Okay, the next one is let's add to our minimum heap as a starting point. So we need to choose we can add any random point, right? In our case, we are going to add the first one. So we are adding the first one, 0 and 0. We are not adding yet, but we are adding, but we are going to calculate its distance to other vertices in a minute. So now we can go and check the distance from our point, from our vertex to all other vertices, right? Let's do that. Let's do our minimum heap. We are going to explore that until it's empty. It's empty. All right. Empty, right? Until it's empty. And until it's not empty, what we are going to do, first thing is let's pull whatever we have in the minimum heap. So basically we are taking now the vertex with the minimum weight. So let's do that. So from our minimum heap, we are pulling our vertex with the minimum weight. So let's just call it, it's going to be array of integers. Let's call it current, right? And for the current, the first element of it, the first element is gonna be our vertex, right? It's gonna be our vertex. So we are taking current 0, right? We are taking current 0. And the next one is gonna be our weight. And it's gonna be our current 1 we are taking here. So we are taking, and before checking that the distance from this vertex to all other vertices, what we need to do, we need to check first we need to check that have we already visited that, right? If we already visited our vertex, so if we already visited that, so what we are gonna do, if it's in our visited list, so we are just continue, we are going to skip that, right? We are going to skip that vertex because we have already explored that. If we are not, we need to mark that as a visited. So we are going to, in our visited, we are going to mark our vertex because we are visiting it right now. Let's just set it to true right away. And also, we need to add that to our minimum cost that we are going to return. Here, we need to create one more variable. Let's just call it int minimum cost, right? Initially, let's set that to 0. And here, for the minimum cost, we are adding the value of whatever the weight is here, right? Because this is the vertex that have not been visited, and it has the minimum weight. Okay, so we are adding to our minimum cost, and now let's go and explore the distance from that vertex, right? From that vertex to all other vertices. So that's what we are gonna do. Let's do that in the, so basically we are taking in our for loop, right? Int I, let's use the for loop, and the I is less than 2, I is less than, so I is less than points length, right? So this is basically the size of our how many vertices we have. So I plus plus, and what we do here, again, we are checking that if we already visited that vertex, right, we don't have to calculate the distance to that vertex because we already visited that. So we are checking that if we already visited that vertex, let's skip it. If we have not visited, right, what we are going to do, we are going to calculate the Manhattan distance. So to do that, let's call it the distance, right? And for the distance, we are going to take the absolute value of, so from our current vertex to all other vertices, right? So we are going to check that the points, right? Points I, first the distance of x, right? And minus, so we can copy paste that here. Vertex, right? Vertex. And we are adding to that plus. So we are taking absolute difference of x1 minus x2. And also we are taking here y1 minus y2, right? y1 minus y2, right? To the vertex. And after calculating that distance, we are adding now to our minimum heap, right? Minimum heap. We are offering or adding, we can use any method. So we are adding a new int, right? New int with the I, right? With that vertex and distance to that vertex, right? We are adding here distance. Okay, so we are adding distance to that vertex. And that's it. Once we exit this loop, once we exit this loop and once we exit this while loop, now we have the minimum distance from our, so we have a minimum spanning tree basically. So we are returning our minimum cost. Okay, let's run it. Okay, here we forgot to add new, right? Here we forgot to add new, and also it should be I here. We are checking that from distance from vertex to all other vertices, so it should be I. And let's run it. Yeah, it should be empty. Okay, it works as expected. Now let's calculate the time and space complexity for our solution. So what's the time and space complexity for in this case? The time complexity is that we are visiting all nodes, right? We are visiting all vertices. So the time complexity of it is weight plus edges, right? Plus edges. And also we are using a priority queue here, minimum heap. So in this case, the time complexity of adding and removing elements from our priority queue is log of n. In our case, it's a log of v. V is the number of vertices, right? It's multiplied by log of v, right? Log of v. So how about the space complexity? Space complexity is, in our case, is determined by by our queue, by our minimum heap, and by array of Boolean. In both of these cases, it's going to be the maximum size of it is the size of our vertices. So how many vertices we have. So our space complexity of v. Okay, that's it. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.